Okay, over this video, we're going to explain and work through conjugate root theorem. And what is this theorem? How can we use the conjugate of complex numbers to find the factors of a polynomial? So, first we're going to revise what conjugates. Complex conjugates is the same number, but the opposite sign of the imaginary components. We normally use the bar to indicate that's the conjugate of z. So z bar means the conjugate of z. So this is just revision what we've did. So for example, if you have the complex number 4 plus 3i, then the conjugate for that will have 4 minus 3i. How are we going to use that for the conjugate root theorem? Now let's take an example. So this one here, you've got the difference between two squares. So we've got obviously expanding that, taking the square root of the first number, the square root of the second component, and then you just say x plus 3, x minus 3. When you expand, you will get this. But what happens if this 3 is imaginary? So 3i instead of 3. So if we have x plus 3i and x minus 3i, if you expand this and simplify it, you will end up with x squared plus 9 minus 1. Expanding this will give me x squared plus 9. Remember, in year 12 and year 11, we used to say this cannot be factorized, but now you can factorize it. The only difference is the factors are imaginary factors, not real factors like this. Okay? You can notice that this polynomial has no I components. So if I look at x squared plus 9, there is no I. But the factorization has I. Because of that, you will see those two factors are conjugate of each other's. And that's what the conjugate root theorem. If the polynomial has no I, but can be factorized over using the complex numbers, then their factors must be conjugate roots. Now, for example, in here we've got x squared plus 1 plus I. Now, plus 1, sorry. X squared plus x plus 1. So to factorize this, to solve this, we're going to use the quadratic formula. So basically, just substituting a and b and c. So we've got substituting in here. And when you substitute, you will see I've got square root of negative 3. And in the previous, in year 12, remember, we used to check if there is no solution for a complex, for the polynomial. If you looked into b squared minus 4ac, we used to give the value of that, and if b squared minus 4ac equals 0, mean it has one repeated root. If b squared minus 4ac greater than 0, that means has two real roots or real solutions. But if b squared minus 4ac, we used to say less than 0, we used to say there's no solution. But now there is a solution. But the solution is not real solution, it's a imaginary solution. So how to solve this? We will get instead of square root of negative 3, we will write it as square root of 3 times square root of negative 1. And that gives me square root of 3i, because remember I is the square root of negative 1. And that's now how you find this is the solution for this equation. Okay. Now you notice that again this solution has a conjugate. So this is these two conjugate roots. The first root is plus square root of 3i over 2, and this is minus square root of 3i. So there's two conjugate roots because the polynomial has no imaginary component. Now, if we have those two, if you expand them, you will end up with the same equation. And you'll see you've got the same equation. Now, find the polynomial over complex. Mean it's a complex number. It's over complex mean the answer or the polynomial that you get will have an imaginary component. So because you want to find the polynomial has two roots, so you're going to rewrite the roots first as factors. So it will be x plus 1 and x minus 1 minus I. Just changing the sign, write them as factors. Now expand, simplify. You will end up with a polynomial but has I components, because I said find the polynomial over C, mean complex numbers. Now, but if I change, the question says, now find the polynomial but over R, real numbers. Because over real numbers means I don't want an I component in the final answer of the polynomial. So to achieve that, you will add another factor, which is the conjugate of that, which is 1 minus I. Now rewrite all the factors, all the roots as factors. So x plus I plus 2, x minus 1 minus I, and x minus 1 plus I. Expand and simplify. So expand, simplify, you'll end up with a polynomial with degree of 3, and it's over R, mean has no I components. So look at the difference. This one here, we did not use the conjugate roots, and we'll end up with a polynomial with an I components. But if we use the conjugate root for that, we will end up with a polynomial with no I. Now you can also use this using the long division if you want to expand it, and you can get that. Now find the roots of 2x to the power of 3 minus 3x squared plus 8x plus 5, giving that 1 plus 2i is a root. Now, because you can see the polynomial has no imaginary components, that means that is the other roots for this polynomial is the conjugate of that. So if we take the conjugate of that root, it's 1 minus 2i. Now rewrite both roots as factors, just changing the sign, put them back in brackets, and now expand. You will get a polynomial with an expand, simplify, you will get a polynomial over R with a degree of 2. So it's a quadratic. Now, this is a polynomial degree of 3, so that means there is 3 solution or 3 roots. Now we already got 2 roots in here, we expanded them, we got this equation. If you use the long division, dividing this one here by that, then you will get the third root, and that's what you can use in here. Get the third root, use the red division, and that's what you get the third root from. Okay, so you've got the 2 roots, and now if you divide this, I'm not going to go through the long division, it's just because we've already did it before. But if you do the long division in here, and you will end up with the third root. Okay, thank you for listening.